non-magnetic self-assemblies. I will also briefly, partially continue on aerosol nanoparticles based on the previous talk, and try to give you an overview of our work, not going into all the details of the measurements. So here is the outline of this presentation. I start with the introduction, and then talk about the novel characterization technique we are developing. Then briefly talk about the magnetic characterization of our structures, and then move on to potential functionalities that we are exploring from these structures, and then finish this presentation with the summary. Magnetic one-dimensional structures, particularly one-dimensional assemblies of particles, are getting more and more attention. There are many reasons behind this. One reason is that while single particles, the magnetization might be fluctuating out, might be forming vortices. If we arrange these particles into one-dimensional assemblies, we give them a kind of anisotropy to the magnetic properties that makes the magnetization much more stable. And that is very important when you want to apply torque or magnetic force on these non-objects. On the other hand, we have magnetic nanowires that are also one-dimensional, and they have a very robust magnetization. But in that case, then we have to go through a multi-step processing technique using template-assisted methods to grow these nanowires. So the synthesis of nanochains is much more easier in that sense. Because of this, magnetic one-dimensional structures have found many potential applications, like in drug delivery, where the drug is loaded on these structures and carried inside the biological system. And by rotating these structures, because we have a magnetization there, one can release the drug. Also, in microactuators, also we want to modulate the optical properties of materials and plasmonics and so on. For synthesizing these structures, there are many methods, several methods developed over time. One major route is the synthesis of nanoparticles or drop casting of nanoparticles under magnetic field that usually ends up having these dense arrays of nanochains, which is not desirable. And then we have to add surface modifiers, or better say, impurities to the system that might degrade the magnetic properties. There are also gas phase techniques developed. However, since the controlling of gas phase particles is much more harder, then controlled deposition of these particles into one-dimensional structures is challenging. There are also lithographic patterning techniques developed. Although these techniques give us very nice arrays of chains, but then they're not scalable, and they're also not very cost efficient. In the previous years in our group, we have developed a new methodology, which is based on the generation of aerosol charged magnetic particles, and then depositing the particles under electric and magnetic fields. And this technique gives a very good control over the deposition of nanoparticles into nanochains uniformly distributed on the surface. And here is the identical location SEM image of a single nanochain as it is growing over time, as we are adding more and more particles to the substrate. Also, since the electric and magnetic fields are decoupled, one can grow the chains lying on the surface or perpendicularly standing on the substrate. If we take one step back, we have the particle generation system. In principle, any technique that can generate particles in the gas phase can be used, but we are using a spark ablation method. In this technique, we start from anode and cathode, repetitive sparks or electric discharges evaporate materials. Initially, the evaporated materials form agglomerates. The agglomerates are passed into a neutralizer. By this, we give them a known charge distribution to the materials. Then we reshape the agglomerates into fine nanoparticles by heating, and then we size select the particles to our desired size and deposit the particles. In the spark ablation technique, we have a good control on the composition of particles, single component, and also multi-component materials can be generated. For example, by putting together the same electrodes, we can have single element nanoparticles like cobalt and nickel. Here you see the deposition of first cobalt and then nickel on the same structure. And then we have also, we can put together different electrodes to have alloyed materials, for example, here, for example, iron, cobalt. Another tuning knob here is the carrier gas. By introducing oxidative or reductive environment, one can generate oxide or metallic nanoparticles. So now let's briefly look into the magnetic properties of these structures. If we collect the particles only with the electric field, we assemble the particles into randomly shaped structures. Now, if we take hysteresis loops of these structures, which is magnetization per magnetic field, in two directions, we take the hysteresis loops in two directions to see if we have any sort of anisotropy. We see that both loops match each other, meaning that there is no anisotropy in the system. And also, what's important here is the remaining magnetization in the system is very low, around 0.3% or 30%. But if we arrange the particles into parallel chains, do the same measurement, we see a very good anisotropy in the system, which comes from the elongated shape of the structures, and we have around 70% remaining magnetization in the system that is needed when we want to play with the magnetic structures by force and torque, meaning that we have achieved this stable magnetization in the system. We're also studying magnetization reversal in the nanoscale of in the single nanochains. Here is the SEM image of the structures, nanochain 1, 2, 3, and then we have the magnetic contrast coming from a 6M XMCD imaging, is where we image the structures with right and left circularly polarized X-rays and subtract the images. So we are changing the magnetic field and then looking at the magnetization, the magnetic contrast. So I'm not going into details, but here we have plotted the average magnetic contrast over magnetic field. And what is important here to note is that although we have different morphologies here, but still the three chains, the hysteresis loops are more or less following each other, which is important to us. We're also doing micromagnetic simulations on these structures. So if you look into the literature, what people are doing is to do the simulations on very idealistic structures, which if you want to compare the simulation results with our experiments, they really do not match. So what we are doing is to develop algorithms that can rebuild our experimental structure and make a three-dimensional model of our system, and then we run our micromagnetic simulations to look into the details of magnetization reversal process and see how the morphology is affecting us. And what we realized was that although the two chains, for example, here, these two examples have almost the same hysteresis loops with same magnetic parameters, porosity, and also remaining magnetization, each of these chains follow a unique magnetization reversal because of their unique morphology. So to this point, I showed you that by this technique, we have a good control on the deposition of nanoparticles into chains and also the composition of the particles. But the key advantage of this technique is that it allows the direct integration of the structures onto any substrate. And this brings forward many possibilities for us now. So if we look here, we have the deposition of iron cobalt nanoparticles on a lacy carbon. And what we see is that the chains are transversing the holes and freestanding in vacuum. So this capability can be used, for example, to make devices to directly integrate one-dimensional structures into devices to, for example, have magnetoresistive devices where the magnetization state and their electrical resistance are coupled together. And this can be used as a basis of some sensing applications. One can also, only by changing the design, go to single chains, which is now interesting for fundamental studies that we're doing. Another capability that we are exploring is the direct integration of these one-dimensional structures into soft polymer layers, which might have many applications in biomedical engineering. And the idea is that if you make a polymer layer magnetic, then we can control its motion, its twist, bending remotely with a magnetic field. So we are working on this. This is a sample prepared by this technique, and our technique is much more easier than the current methods, where we deposit the structures and then laminate our sample. If we now keep the magnetic field in the magnetic field and apply the field, we see the bending of the film, which is because of this robust magnetization along the film that allows the effective torque applied on the film. And the important thing here is that since you're not relying on templates and the small chemical batches, it allows tandem or continuous production of these magnetic films, which is not achieved yet. As a summary of this, I hope I could show you that the technique allows the facile fabrication of one-dimensional structures and also the direct integration of these structures into different substrates. Have good control on the composition, and the magnetism of these structures is also what we expect over the anisotropic magnetic properties, and also the technique allows multifunctionality of the structures. At the end, I want to thank all the people involved in this work, and thank you very much for your attention.